All right, so welcome back. Is the volume all right? Okay. So we printed off, Sasha printed off some copies of the exercises. So I think the people toward the front got some copies, but maybe I'll send a couple this way and a couple this way, and don't. We printed off. Maybe you can share them a little bit to save paper. And they're also available online, and so it has the exercises that we're mentioning as we go in a little more detail, a little bit more clearly for you to contemplate throughout the day. Right, so as Sasha said, the derived category starts life in the 60s as a bookkeeping device for homological algebra, and by the 90s, 2000s, it comes to be seen as a thing with important geometric content. So today and tomorrow we're deeply into the bookkeeping and homological algebra, and hopefully by the end of the week we get into some geometry, and next week for sure. Right, so my first goal in this hour is to prove what Sasha said at the end about quasi-isomorphisms being a localizing class in the homotopy category, and then to talk about ext extensions and maps in the derived category. And the tool that I need is cones. So that's what I'm going to talk about for a little bit. So the definition, so given a map F from A to B, a map of complexes, so a chain map like that, we define the cone of F. Boy, this chalk will really slow me down. As an object, as a complex, well, the terms in the complex are, Sasha, did you talk about shifts? You didn't talk about shifts, no. Well, maybe even before that. Well, is A shifted by 1, this is a square bracket, plus B, so let me tell you what that means. That is, it's going to be a complex whose ith term is the I plus first term of A, direct sum the ith term of B. And I need to tell you what the differential is still. With differential given by minus dA F0 dB. Right, so this goes from AI plus 1 to AI plus 2. This goes from AI plus 1 to BI plus 1. You get the idea. So you can check that d squared is 0. And I should tell you the reason for the name of this. So the reason for the name is that in topology, if you have a map of spaces, f from x to y, and the picture everyone always draws is x is a circle and y is a plane, and you embed, and f is some wiggly embedding like that. You can form, the cone of f as a space is you take x cross the interval, disjoint union with y, and then you glue x0 to x prime 0 for all x and x prime in x, and x1 to f of x, which is in y. And so the picture is you take the cone on F, like that. And then I won't write it, but the fact is that if you take the singular chain complex of X and the singular chain complex of Y, and the induced map F on singular chain complexes, then the cone of that induced map, this homological cone, is going to be quasi-isomorphic to the singular chain complex of this thing. And so that's the motivation, but you can also just use it. So if you want to read about some of the, we're going to take a very algebraic perspective in almost all of what we do for the first couple days, but homological algebra is also a part of topology, so if you want to read Hatcher or something like that, you'll also learn something there. Okay, so observe that if A and B are single objects, if A and B are just single objects, right? So I just have so we'll often identify an object of our original category with the chain complex that just has that object in degree 0. We want to be flexible in going back and forth between those two. And then you have this F. Then the cone of F is this complex. And maybe I'll underline what's in degree 0. That's what's in degree 0. So in particular, so H minus 1 of the cone is the kernel of F, and H0 of the cone is the co-kernel of F, which is by definition B mod the image of F. So you want to think that, in general, the cone is sort of kernel and co-kernel mixed together like a snake eating its tail. So next, are there questions about anything so far? So next, we have a short exact sequence, of complexes. B includes into the cone of F. Right, so now we're back in this general setting here. We're no longer just single objects, but we're general complexes. B includes in the cone of F, and cone of F maps to A shifted by 1, which I guess I should now really define properly. So where by definition A shifted by 1 is the complex given by whose its ith term is the I plus first term of A, and it's convenient to have to flip the sign of D for reasons that we'll get into. And if you sit and think about it, you'll realize that shifting by 1 has the effect of moving all the terms 1 to the left, not to the right, which is irritating the first 100 times that you see it, but on the 101st time you make your peace with it. Right, so that's the shift of a complex. You can shift them to the left and the right. And what does it mean to be a short exact sequence of complexes? It just means that term by term, no, I'll do it here. Well, term by term I have, think of B as running up and down, and the cone of F is running up and down, and A is running up and down, and I have maps of complexes, and each line is a short exact sequence. So you sit and look. Well, of course, it's a short exact sequence because the middle thing is the sum, and then you check that it plays nicely with this differential. And so why do we want that? So thus, we get a long exact sequence how should it go? We'll have hi of the complex B to hi of the cone to hi plus 1 of A, right? So you can check that hi of A shifted by 1 is hi plus 1 of A. And if it comes back this way, hi of A, hi minus 1 of the cone, and so on. So from a short exact sequence of complexes, you get a long exact sequence in cohomology. I don't want to prove that. You can read that. If you're not already sick of it, you can read it in any book on homological algebra. You could read it in Hatcher, you could read it in Weibull, any of these places, how to do the snake lemma that gets you, like this map is the interesting one, right? And as a corollary, which we'll want to use a lot, corollary is that F is a quasi-isomorphism if and only if the cone of F has no cohomology, i.e. Cone of F is quasi-isomorphic to 0. Or we'll say it's isomorphic to 0 in the derived category, where A is our abelian category. Yes? Yeah, well, it is, but that's something to check, right? So that's a great remark. Do we have any colored chalk? We don't, so you can check. So you could check if you want that this is hi of F. That's a good remark. But you can see from the way it's set up, there'd be something to check. And I want to call this acyclic. So cone F. So we'll say that a complex is acyclic if it has no cohomology, if it's quasi-isomorphic to 0. And now we want to remember our goal is to prove this thing that Sasha promised. And also we're going to use cones all the time for everything. So here's a proposition that we need. Let me give this map a name. Let me call this map tau. So proposition, the cone of tau, and I'll write it a little bit, B via tau to cone of f, is quasi-isomorphic to A shifted by 1. So if you have, from two things in a map, you get a cone and some maps continuing around. And then if you take the cone of the cone, you just keep going around and around the circle. This is true in the homotopy category. So not that it's quasi-isomorphic, stronger than that. It's true in the homotopy category, K of A. So let me sketch the proof for you. There's an obvious inclusion. I'm not going to take the obvious inclusion. We have a map from A of 1 into the cone of tau. And that I'm going to write down for you in components in just a second. And then there's just a natural projection. Excuse me. So I'm going to take two maps like this as follows. So first, so what are we talking about at chain level, or at, what are the terms of these complexes? We need a map from A I plus 1. Well, what's the cone of tau? What's the ith piece of that? It's the I plus 1th term of B plus the ith term of the cone of F. So that's going to be AI plus 1 plus B. So this here is cone F, the ith piece of it. And then I'm going to go back like this. And the map here is going to be given in coordinates by, I'm going to take minus F from AI plus 1 to B, and 1 from AI plus 1 to itself, and 0. Oh, sorry, this should be BI, shouldn't it? And this map is just going to be projection onto the middle factor, is what you would guess. And what are the differentials in these complexes? So this is supposed to be a map of complexes. So what are the differentials? The map here is just minus the differential on A. And the map here is a little more complicated. It's minus dB, minus dA, dB like that. And here we have F. And because tau, I didn't write it, but it's the only thing it could possibly be, which is here we have the identity map from this BI plus 1 to the BI plus 1 that's going to be there. So I can write more if you want me to. I don't want to overload you with things to write, but I also don't want to write so little that you don't know what I'm talking about. So is it clear what we're talking about? A shifted by 1 is this complex. The cone of tau is this complex where I'm going to have BI plus 2, AI plus 2, BI plus 1. And the differential is given like this. If you unwind the definition. And here you get the idea. And I claim that this is a chain map. And clearly, if I go if I go from here to here to here, that's the identity. And so then the claim so I guess I should say check that these are chain maps. And then the next claim is that the composition from cone of f to AI, to A shifted by 1, excuse me, back to the cone of f, that this composition is homotopy equivalent to the identity on cone of f. So exercise is to check. I think this one I actually wrote in the exercises carefully enough that you can check it. Thank you, cone of tau. Just take a check here for a second. So there's lots of little bits of bookkeeping here. And we can say a little more. So moreover, well, let's see. We have this short exact sequence, cone of f goes to cone of tau, goes to b shifted by 1. This is our favorite exact sequence that gives us the long exact sequence in cohomology comparing the three things. But we could also write, we have a map from cone of f to a shifted by 1, and this is our quasi-isomorphism that we just wrote down, or our homotopy equivalence that we just wrote down, stronger than a quasi-isomorphism. This goes to b shifted by 1, so these are the same, and here I'm going to put minus f. This commutes. Right, so the standard short exact sequence of complexes for the cone of tau, we said the cone of tau is the same as a shifted by 1, and it's related to this complex that we know and love. So I don't want to check that in public. You don't get anything by watching me check that, but you will get something by checking it yourself. As I was preparing this, I haven't sort of checked these diagrams in many years, and it is kind of fun to mess around with a couple of them to get the flavor of it. This one really commutes. That brings me to my next point, which is that, this, if I try to run it the other way, maybe rather than write the whole thing again, but if I put this one here, but this only commutes. So if I go up instead of down, this only commutes up to homotopy. Right? And in particular, it's this square that's the problem. Because these two maps that we've written down that we're talking about are only homotopy inverses, not, of course, they can't be actually inverses in the category of complexes because this complex is so much bigger than this complex. And this is, you have an exercise about why quasi-isomorphisms are not a localizing set in the category of complexes, but only in the homotopy category, and this turns out to be the key point. So now, Sasha promised a number of things. Unfortunately, I'm going to transpose his diagram just to piss you off. If I call this F and it's a quasi-isomorphism, and G, like this, then the claim was that there exists something here and maps like this, such that this one is a quasi-isomorphism. So this is what we need to be able to invert quasi-isomorphisms, and this will again be in the homotopy category and not the category of complexes. And he promised you 3 different diagrams. I'm going to check one of them for you. And if you want to read, you can either read Gelfand and Manin or Huybrecht's Fourier Mukai book, which I think we've sent you proper references to both of those. Okay, so let's do it. We have X going via F to Y. These are complexes of modules or sheaves or whatever. And then we have this map to the cone of F, tau. And that maps to A shifted by 1. And this is one of these diagrams that you can only understand if you watched it being drawn. You can't, if you come in the room in 5 minutes, you won't understand the diagram, right? I want to factor this vertical map from Z. This kind of Z. I want to put another copy of Y here. And this is going to be G. So we have a map from Y to tau, the cone of F. This is the same thing. And here I want to put the cone of tau. And here we have this homotopy equivalence. And remember, this square only commutes up to homotopy. Yes? Yes, X, thank you. And here I again want to put cone of F. And so this map had better be tau after G. And here I'm going to take the cone of that. So remember, this is all in the homotopy category, yeah. Well, the asserted commutativity is all in the homotopy category. But the problematic square is that one. And now you can check that there is a map like this. So there exists a map here. Just whenever I have two things mapping to the same thing, then there's a natural way to map the cones. So this is also fun to check. I would say of the 5 things that I'm urging you to check, you should check maybe 2, but each of you a different 2. Right. So, and now I can bring, cone of tau then maps to y, right? Remember, cone of tau, at least as far as its terms, it's this plus that. So I can bring that over here. So this could map to y shifted by 1. So I'm going to bring it over here. Cone of tau minus 1. And this is still, essentially I'm just copying this set of arrows over here. And we asserted that these squares all commute up to homotopy. And I can also put cone of tau g shifted by minus 1 here. And this is that same map from over there. So the obvious map that you come up with, mapping from there to there, also makes this square commute. It's this square that only commutes up to homotopy. Okay. So the thing that, I'm sorry this is such a mess. The thing that we want is these 4. We were given f and g. And so the claim is just that, that this should be a quasi-isomorphism. And how do you tell if something's a quasi-isomorphism? You ask whether its cone is acyclic. Right? But this, so f was a quasi-isomorphism. So we're using 2 things that we've just done. One, we observed that because f is a quasi-isomorphism, cone of f is acyclic. So this is acyclic. Right? It has no cohomology. So the thing to check then is that the cone of this is really the cone of this map. And is that what we already checked? So there I think that is what we already checked. So there are 3, the cone of the cone is the cone. And so it keeps going around and around and around. And I think we checked the first leg and not the second leg. Right, so maybe let me just write a few words. The cone of the red arrow here is the cone of f, which is acyclic. And so the red arrow is a quasi-isomorphism. And that's the end of the sketch proof. And this, okay, I'm going to write up an exercise that's in there because I think it's worth seeing right now. I won't solve it. Why do we have to go through all this rigmarole? You might say, couldn't you just have taken some kind of fiber product of x and z over y, and surely that would have been the right answer? And it's not the right answer. So exercise. In the category of complexes of abelian groups, you can't fill in this diagram. So I'm going to have 0 mapping to the 2-term complex z goes to z via the identity. So this is a quasi-isomorphism because this thing has no cohomology. And here I'm going to take this complex and map it in the obvious way. And so there's nothing you can put here so that this is a quasi-isomorphism and the thing commutes on the nose. You have to do all this up to homotopy business. So in particular, the fiber product of these two doesn't work because that would make it commute. And if all this business about quasi-isomorphism seems, inverting quasi-isomorphisms and all the bookkeeping, it's a little overwhelming the first time you see it. But you rarely get, in practice, you rarely get this far down into the weeds, this far into the guts of the machine. So it's good to know that it's all there. Question? Yeah.
So that statement you made about the cone of the red arrow being in front of that, that's not directly a composition, it's like a modified version?
Well, let's think. So I guess what I proved is that the cone of this arrow is z shifted by 1, yeah? Right. And so to say that the cone of this arrow is the cone of f is a similar kind of thing. It's exactly the same flavor. Yeah, but it's true there are two different statements there. All right, so we have, all right. So in only an hour and a half of sketching, we have the derived category. The thing where quasi-isomorphisms become isomorphisms. And so in particular, every sheaf or module or whatever becomes isomorphic to any projective resolution that you might like, or any injective resolution, any resolution by vector bundles or flat modules or whatever. If you have one object, you take any resolution of it. They're all quasi-isomorphic in real life, and so they're all isomorphic in the derived category. And that's what we mean when we say that it's a bookkeeping device for homological algebra. So our next goal using cones so let's let A be an abelian category. And again, your favorite abelian categories, if you don't like the generality, your favorite abelian categories are modules over a ring, or coherent or quasi-coherent sheaves on a variety, although there are many others. So let A be an abelian category. Let A and B be two objects in A. Then the X groups, Xi in that abelian category between A and B, is naturally isomorphic to Hom in the derived category of A between A and B shifted by I. So I defined for you what it means to shift by 1. You can imagine if you shift by 2, how that would work. Yes?
This category have like enough injectives or enough projections?
Let's say with enough, yeah. With enough injectives or projectives. Right, so this is the second thing we want to do this hour, is understand X's and actually maybe I shouldn't put that up yet. We want to understand X's and Homs in the derived category and what they have to do with each other. So this category, the derived category, really knows a lot about homological algebra already. And now that we have enough cones, we can do it. So recall how to compute X die. Right, so we replace so we do a resolution. Well, we can either resolve A by projectives or B by injectives. So A would come from P naught, from P1, from P2, and so on. These are all projectives. Or you should resolve B by injectives. Should I remind you the definition of projective and injective object? How many would like to see the definition of an injective object? Okay. Third. Let me just say one word about it, because we're going to use them a lot. Your favorite projective object is a free module over a ring. So if you're totally happy with this, don't write it. So projective just says that if I have a map from X to Y and I have a projective here and a map like that, that I can lift it. Does this need to be surjective? Yeah. Right. And so if this were a free module, you would just take wherever your generators of your free module land there, and you pick some elements of X that hit them, and then you just lift like that, and you can just do it. But you don't really need, for all of homological algebra, you don't really need a free module. You just need that this diagram works. So we define a projective to be the thing where you can do that. And injective is the dual thing. If I have X injecting into Y, and I have some injective object like this, and there exists a map like this. Have I got that right? And these things are sort of huge and terrible to think about, but the point is, in the category of sheaves on your favorite variety, especially if it's a projective variety, there tend to be no projective objects in the category of sheaves, unless it was an affine scheme, whereas there tend to be lots of injective objects, but they're huge and scary. Okay. So that was that. And if you're rusty on that kind of thing, again, you could go read Weibel or one of these books, or you could Google. Actually, Dummett and Foote has a nice discussion of this if you prefer that. And so you take. I'm going to focus on the first one, because when you're doing rings, that's just much nicer. You sort of never write down an explicit injective object. But for all our formal stuff, we're going to prefer injectives to projectives. So you resolve it like that, and then you take Hom from everything to B. So you get a complex like this, 0 to Hom from P naught to B, to Hom from P1 to B, Hom P2 to B. And this is probably not exact anymore. And so the kernel of this, you check, is Hom AB. But H1, we define it as X1 AB, and H2 and so on. And if your only exposure to X so far in life is the universal coefficient theorem, you may be surprised to hear about X2. Because if you're working in abelian groups, everything has a two-term free resolution. And so you get x1s but never x2s. But when you work over bigger rings, essentially it's because Z is a one-dimensional scheme. And if you work over a higher dimensional scheme, then you get more and more of these x's. And we'll see that as the week goes on. So I need a proposition, which is I'm not going to prove, but it's going to follow from what Sasha does after lunch. And that's if I have a map, if I have a quasi-isomorphism, and I is a complex of injectives, or projectives, but again, we're going to focus on, well, I leave it to you to rewrite this the other way. Then the map, then you get some induced map homomorphisms in the homotopy category between B and I. You get an induced map from there to homomorphisms in the homotopic category between A and I. This is an isomorphism that, so this is some technical thing that either Sasha will do or it will follow from what he does. And the correlate, that's what I'm saying next. And so corollary, if A is an arbitrary complex, and I is a complex of injectives, then Hom in the homotopy category between A and I is the same as Hom in the derived category between A and I. Right. So this is what you've seen a little bit, and you'll see in the exercises that in general, you may have interesting maps in the derived category that just don't come from the homotopy category. But if your target is a complex of injectives, or if your source is a complex of projectives, then that doesn't happen. So why does this follow? What a map in, how's my time? I'm all right. In the derived category of A is, you have your A and your I like that. And I don't just go straight there. First, I go via some quasi-isomorphism from B, and then I go directly from B to I. But this previous proposition says that maps from B to I are the same as maps from A to I. Sorry, I guess I've got it going backwards there, but that's all right. And so maps in the homotopy category from A to I are the same as maps in the homotopy category from B to I. You get it? Okay, so you'll get to digest some more of that next time. the point is Hom in the derived category is what you're interested in, and Hom in the homotopy category is what you can compute. And complexes of injectives make them the same, or projectives. So now let's come to the punchline, which I erased. So the punchline is that Hom in the derived category from A to B shifted by I is X'd I in the original category from A to B. So proof. Let's take an injective resolution. Resolution, 0 to B to I naught. And you could do it with a projective resolution too. And in the exercises, all the examples you do in the exercises, you'll want projective resolutions or something. Right? So this map I think it's worth drawing this diagram a couple times. This is a quasi-isomorphism. Right? This is what we keep saying about how your object becomes isomorphic to its injective resolution in the derived category. And then, so maps in the derived category between A and B shifted by I are the same as maps in the derived category between A and this injective complex shifted by I, which are the same as maps in the homotopy category between A and your complex shifted by I. Of course, you shift a complex of injectives, it's still a complex of injectives. And what is that? What is a map from A to that injective complex in the homotopy category? So here's A. And here's my injective resolution shifted by I, just to give you a feeling of how this works. So in degree 0, we're now going to have the ith piece of that complex, going to the I plus first piece and so on, coming from the I minus first piece, and so on. Yes, please.
Do we take this injective resolution of B at every part of B? Like, is B a complex?
Oh, no, A and B are just objects in the category. They're just single objects, yeah. Yeah. Yeah, so the point of this is to, well, and Sasha's going to get into that more, how to take a complex and resolve it by injectives. But so far, we're just relating good old X'd, good old homological algebra to this big machine that we're developing. Yeah. Thanks. So what is a map? What is it? So chain maps, mod chain homotopies. So if I want a map like this, that's an element of Hom from A to II. Maybe I'll call this F. And I want that to be a chain map. So in particular, this square needs to commute. Right? So D after F needs to be 0. So F needs to go to 0 when I compose with D. I plus 1. That's saying that I have a chain map. It's saying that F is in the kernel of the induced map here. And what does it mean to say that I'm going to mod out chain homotopies? So if F is DH plus HD, right, then that means I need to kill the image of this. So H goes to D after H. Right. So chain map, so stupid maps of complexes that don't do anything would just be right there. Chain maps are the kernel of this, and things that are chain homotopic to 0 are the image of that. So maps in the homotopy category are the kernel of that mod the image of that, which is exactly xi. Let me not write too much. Maybe to give, so you'll have an exercise which is to take your ring in a polynomial in 2 variables, and let's also say that K is just the residue field, R mod X and Y. And you can compute that x2 of K by itself is K. So there are some non-trivial extensions, and you'll want to understand them in these kind of terms, only with free resolutions instead of injective resolutions, because those you can really write down. Right? And this is HOM in the derived category of R modules between K and K shifted by 2. But of course, HOM in the homotopy category between K and K shifted by 2. Well, here's K. And here's K shifted by 2. And you're just not going to get any interesting maps like this, right? So it's only when you resolve one of them with some quasi-isomorphism and then get a map from the bigger quasi-isomorphic thing to the other that this is 0. So in particular, this is an example of a map in the derived category that induces, so if I get a non-trivial extension here, then I have a map in the derived category which is not 0, but its induced maps on cohomology have to be 0 because there's just not very much cohomology there. So here, the induced maps on cohomology are all 0, even though the map isn't 0. Okay. Let me stop there. You have some exercises to look at, both from last time and this time. Have those made their way around? Do we need some more copies? You need some more. You need some more. Okay, we'll go run off some more. Right, thanks. And then at noon, we'll go to lunch.